Hello everyone, I hope you're having a great day and you're ready to learn something new about solving systems of linear differential equations. Up to this point, we've learned how to solve systems by substitution or elimination and also using linear differential operators. In 5.4, we will learn the eigenvalue method for homogeneous systems. This method will be reminiscent of finding the characteristic equation for a single differential equation, but we're going to be applying that process for all of the equations in the system at once. So part one, let's start with a little background. Here's the development of the process. Consider a first-order homogeneous system of the form x bar prime equals ax. Now remember, the bold print indicates that we're dealing with a column vector. When we write it by hand, we put a bar over it or a vector hat over it. A is a square constant matrix. That's going to be the coefficient matrix. As we did with single differential equations, we're going to assume a trial solution of the form x equals v bar e to the lambda t. Now, if you'll remember, for a single differential equation, we made the assumption of the solution e to the rt, and we plugged it into the differential equation, and we were able to derive our characteristic equation in R, and the nature of those roots indicated the form of our solution. So this is essentially what we're doing here, except we're applying it to the entire system at once. Now, if x is equal to v e to the lambda t, then x prime equals lambda v e to the lambda t. V is going to be a vector of constants and lambda is a constant. So assuming this particular solution, let's plug it into the original matrix equation and derive our characteristic equation. So our original matrix equation is x prime equals ax bar. Now remember, the vector hat there is the by hand way of writing the bold print. It indicates an n by 1 column vector. So if you'll remember, x bar contains the dependent variables of the system, x1 of t, x2 of t, up to xn of t, right? So that's what we're looking at there. Okay, so x bar prime equals ax bar. Now, we're going to plug in the assumption or the nature of our solution. X bar prime is lambda v bar e to the lambda t. V bar is a column vector of constants, and remember, lambda is a constant. This is equal to a times x, and we've assumed that x is equal to v bar e to the lambda t. Now, e raised to a power is never equal to 0, so we can go ahead and divide both sides by e to the lambda t to obtain lambda v equal a times v. This is a matrix equation, so we're going to solve this equation to derive the characteristic equation. I'm going to subtract lambda v from both sides. When I subtract lambda v from both sides, it doesn't just leave behind a 0 over here, it leaves behind an n by 1 column vector of 0. So make sure that you get a vector hat on that. And we have av minus lambda v. Both of those have a v in common, and so I'm going to factor it out as if it were a greatest common factor. However, with matrix arithmetic, we have to preserve the order. So I'm not going to factor v to the left. I'm going to factor v to the right side. Now leave a little space here. So I've got v on the right. Now what I have here is an n by n matrix, and lambda is a constant. So what I have written here is not a defined operation. In order for this to be a defined operation, I'm going to have to multiply lambda by a n by n matrix, an identity matrix. Again, much of this information comes from linear algebra, and if you don't have previous experience there, this will be new information. So an identity matrix, for example, let me give you a 2 by 2 identity matrix. An identity matrix is simply a square matrix with ones along the main diagonal, top left to bottom right, and zeros elsewhere. So a 3 by 3 identity matrix would look something like this, okay? The reason that we're using that is because now the operation a minus lambda I is defined. This is an n by n matrix, and this is an n by n matrix. So what we have here is a matrix equation. Now, we can say from linear algebra This homogeneous system has a non-trivial solution provided the determinant of a minus lambda times I equals 0. So again, this is a result from the studies in linear algebra. This is a homogeneous system because we've got all zeros over here on the left side. And results from linear algebra show that such a system will have a non-trivial solution. That means substance to the solutions, not everything is 0. Provided the determinant of a minus lambda I equals 0. Notice this is an ordinary 0 over here. That's the constant 0. Whereas we were dealing with the 0 vector over here, we have a constant vector over here. So in order to solve this system, we need to determine lambda. Those are going to be special values for the characteristic equation. So we need to find lambda. And then, once we know lambda, we need to find vector v, okay? Those are the unknowns in the assumption to our solution. I need to determine this exponent, and I need to determine this vector v. Now, hang in here with me. It's going to get easier as we begin looking at examples. Definition: the number lambda is called an eigenvalue of the n by n matrix A, provided the determinant of a minus lambda I equals scalar 0, where I is an n by n identity matrix. An eigenvector associated with the eigenvalue lambda is the non-zero vector v, such that a times v equals lambda v. That's what we have up here, so that this equation is satisfied. Again, notice the bold print over here that indicates 0 vector. Now, eigenvalue is the word for lambda. Eigenvector is for v. If it sounds like we're talking German, it's because those are derived from the German language. The prefix eigen came from the German language, and it is a word that can be translated as characteristic. So we're talking about the characteristic values and the characteristic vectors. So ultimately what we're doing here is solving a characteristic equation for the entire system at once. Now remember, we previously used to find r's in our characteristic equations for a single differential equation. Now we're finding lambdas and v's, the solutions to the characteristic equation for the entire matrix at once. So let's apply this procedure to actually solving a problem. To solve the matrix equation, x prime equals ax, do the following. Number one, we're going to find the solutions to the characteristic equation. The characteristic equation is the determinant of a minus lambda I equals 0, and we're going to get any number of eigenvalues. Two, find n linearly independent vectors, v sub 1, v sub 2, up to v sub n, corresponding to each eigenvalue. So each eigenvalue will have a corresponding eigenvector. Number 3, express the n linearly independent solutions as x sub 1 equals v1 e to the lambda 1t, x sub 2 equals v2 e to the lambda 2t, so on and so forth. And that comes back to the assumption of the form of our solution. So we're just putting it all together. Now, as we did with single differential equations, we're going to have a couple of cases to consider for our eigenvalues. Recall the nature of the roots of the characteristic equation, which we previously called R, determined the form for the solution. That's going to be true here as well. So we're going to consider two cases: distinct real eigenvalues and complex eigenvalues. Example 1, use eigenvectors and eigenvalues to solve the given system. Now, take a look at this system. It is linear first order. Our independent variable here we'll assume is t. We have two dependent variables, x sub 1 and x sub 2. Basically, the solution to this function, this system is two functions, x sub 1 of t and x sub 2 of t, that balance both of those equations simultaneously. You could probably sit down and solve this by substitution or elimination or using linear differential operators. So the problem hasn't changed. Our approach to the problem has changed. We're looking at a new method of solution, eigenvalues and eigenvectors. Let's begin by rewriting this system in matrix form. So our system could be written x bar prime equals, let's form a coefficient matrix, 4x1, 1x2, 6x1, negative 1x2 times x bar. Now remember, x bar represents the column vector 2 by 1 column vector containing our two functions that solve the system. So here our equation is in matrix form, and now we're going to rewrite this in terms of our development above. We want to write this a minus lambda I times vector v equals 0 vector, where this is vector A. The characteristic equation then is the determinant of a minus lambda I equals scalar 0. So let's develop our characteristic equation. We're going to find the determinant of matrix A, 4, 6, 1, negative 1, minus lambda times an appropriately sized identity matrix, a 2 by 2 identity matrix, equal to 0. Notice what I have left is a determinant. That turns out to be a scalar, and we have a scalar on the right. Now, multiplying lambda throughout our given matrix, notice each entry in the matrix gets multiplied by lambda. So notice we end up with a diagonal of lambdas. That will help you to make shortcuts later on. So simplifying here, we have the determinant of, now I'm going to combine corresponding entries here. So I'm going to take this position minus this position. That's 4 minus lambda, 1 minus 0, 6 minus 0, and negative 1 minus lambda. So when we add or subtract matrices, we just apply that operation to corresponding entries. Now, let's find this 2 by 2 determinant. Recall that when we calculate a 2 by 2 determinant, we find the forward diagonal product and we subtract the reverse diagonal product, and it must be in that order. So our forward diagonal product is 4 minus lambda times negative 1 minus lambda, minus our reverse diagonal product, which looks like 6 times 1. That's equal to 0. Completing our FOIL here, we have negative 4 minus 4 lambda plus lambda squared minus 6 equals 0. And simplifying, we come up with the characteristic equation, lambda squared minus 3 lambda minus 10 equals 0. We can easily solve this by factoring lambda minus 5 times lambda plus 2. So we're going to end up with two eigenvalues. Let's call them lambda sub 1 equal to 5 and lambda sub 2 equal to negative 2. Okay, so we have solved the characteristic equation. This was our ultimate simplified characteristic equation, of course, derived from this pattern. And we ended up with two real distinct eigenvalues. Two real and distinct, not repeated, eigenvalues. So again, these correspond to the previous R's that we used to find for the characteristic equation. Remember that when you find distinct real eigenvalues or distinct real roots of your characteristic equation, those become the coefficients of the exponent. So what we have found here are the lambdas that go up there in the exponent. Okay, so we found those right there. We have two of them. Now we need to find the eigenvectors that correspond to each eigenvalue. So we will begin with our first eigenvalue, lambda sub 1 equals 5. So case 1, eigenvalue lambda sub 1 equals 5. We want to find vector v sub 1, eigenvector v sub 1. Okay, now the way that we're going to do this, we're going to come back up here to our matrix equation. I'm going to set this up, A minus lambda I times V equal to 0 vector. So we need to set up A minus lambda I times V equals 0. We used the determinant of that coefficient matrix to figure out the eigenvalues. Now we're going to use the matrix equation to find the eigenvectors. A minus lambda I, notice, is what we have inside this determinant right here. So I'm going to plug 5 in for lambda in those two positions. Okay, so we're going to have matrix A minus lambda. I'm going to show all the work on this one. A minus lambda, 6, 1, and -1 minus lambda times eigenvector with representatives v sub 1 and v sub 2 equal to, whoops, forgot my vector hat up there, equal to 0, 0. So when we simplify this matrix equation, whoops, I forgot to plug in a 5, didn't I? We end up with something that looks like this. Notice on the left side we're multiplying two matrices, and we've discussed this in previous videos, but we have a 2 by 2 matrix times a 2 by 1 column vector. So the middle two dimensions match, and the result is going to be a 2 by 1 column vector like what we have over here on the right side. So let's go ahead and multiply those matrices together so that you can see what the result looks like. We're actually dealing with a dependent system here. So if I multiply row 1 times column 1, I'm going to end up with the equation -v1 plus v2 equals 0. And if I multiply row 2 by column 1, I'm going to end up with the equation 6 times v1 minus 6 times v2 equals 0. Notice this is a dependent linear system because the second equation is a scalar multiple of the first. That means there is an infinite number of solutions to this matrix equation. I just need to find one. So if I solve for V2 in terms of V1 for either equation, I'm going to end up with this relationship. V2 is equal to V1. So when I determine the eigenvector that corresponds to the first eigenvalue 5, I just have to choose constants that exhibit this relationship. So let's suppose V1 is equal to 1. I could choose any number right here. I could choose 85 if I wanted to. Let's choose something easy to work with like 1. Well, if V1 is equal to 1, then V2 is also equal to 1. So we can say then our eigenvector, our first eigenvector, V1, has these two components, 1, 1. Now again, let me point out about the notation. V sub 1 simply means the first eigenvector corresponding to my first eigenvalue. This one with the vector hat is distinct from this one. This just means the first component of my first eigenvector. Now let's express this as a particular solution. X sub 1 of t then is equal to e to the lambda sub 1t times eigenvector 1, 1. That is one particular solution. So the multiple here indicates that I should multiply each component by e to the 5t. So we end up with this as our first particular solution. Okay, but we have two. We need to repeat this process again for our second eigenvalue. So case 2, we had another eigenvalue of -2, and we need to find our second eigenvector, okay, using the same process. So we're going to set up our matrix equation that we have over here. And remember, I'm looking at this matrix. I have A minus lambda I right here. So I'm going to plug -2 in here and here. Okay, so for our first entry, we have 4 minus -2, which is 6. We have a 6 here, a 1 here. And for the last entry, we have 1 minus -2, which is also 1. So again, notice we are dealing with a dependent system. That means a system with an infinite number of solutions. Because if I carry out this multiplication, I get the same equation twice. which indicates that I have an infinite number of solutions. I just need to find one. So I'm going to choose something easy. Let's let V1 be equal to 1. Then V2 would be equal to -6 times 1, or -6. So my second eigenvector is going to contain components 1 and -6. Now we can determine our second particular solution, x sub 2 of t, which is going to be e to the negative lambda t times v sub 2. Or if I want to write it with more detail, that's e to the negative 2t, -6 e to the negative 2t. Okay? So each of these particular solutions contains a function for x1 and a function for x2. The subscripts with the vectors indicates a solution to the system. Let's put this all together and write the general solution to the system. Our general solution then looks like x bar equal to c sub 1 x1 bar plus c sub 2 x2 bar. Or with a little more detail here, that's going to be c sub 1 times x1 e to the 5t e to the 5t plus c sub 2 times x2 e to the negative 2t -6 e to the negative 2t. Okay, if I wanted to look at it as two distinct solutions with a little more detail, we could see x sub 1 of t is c sub 1 e to the 5t plus c sub 2 e to the negative 2t, and x sub 2 of t is c1 e to the 5t minus 6c sub 2 e to the negative 2t. So that is the general solution to the system. General because I have those arbitrary constants c1 and c2. The benefit of solving the equation in this way is you end up with exactly the number of constants, arbitrary constants you need, and you don't have to work too hard to reduce the number of constants. Again, please understand the subtle differences in the notation here. The subscript here that goes with the bar, subscript here, is distinct from the subscript here that does not have a bar and the subscript here that does not have a bar. This actually means the first function, x sub 1, right, which is this, x sub 2 without a bar is over here. The one with the bar, these two just indicate I have two distinct particular solutions, and I'm putting them together to form a general solution. Okay, let's go through that process again, this time with a bigger system. I'm going to erase some of the information I have over here so I'll have plenty of space to work this bigger problem. So we're going to solve this first order linear system of differential equations using the method of eigenvalues and eigenvectors. So the same thing we did above, just a little bit of a bigger system. So let's begin by rewriting this in matrix form. X bar prime equals, we're determining our coefficient matrix A. Looks like it has constants 3, 2, and 2, -5, -4, and -2, 5, 5, and 3. Because we have 3 equations in 3 variables, we should expect 3 eigenvalues and 3 eigenvectors. So we need to find our eigenvectors. So we'll start there. Find, I said vectors, eigenvalues by solving determinant of A minus lambda I equals 0. So this is matrix A. So I'm showing some fewer steps on this one, but hopefully you're beginning to understand the process. So A minus lambda I, determinant of A minus lambda I, is going to look like a 3 by 3 matrix A minus lambda times a 3 by 3 identity matrix. So just a heads up here, lambda I is going to look like this. I multiply the diagonal of 1s from the identity matrix by lambdas, so I end up having a diagonal of lambdas. So A minus lambda I is going to look like 3 minus lambda, working in our columns here, -5 and 5, 2, -4 minus lambda, 5, 2, -2, and 3 minus lambda. So notice I've just subtracted the constant lambda from the diagonal of our original matrix A. This is our characteristic equation, and we need to solve this for lambda. Notice on the right side we have constant 0, and on the left side we have the determinant of a 3 by 3 matrix, which is also a constant. So to calculate the determinant of a 3 by 3 matrix, I'm going to expand about row 1. You can expand about any column or any row, but for those of you concurrently in Calculus 3 and you've been calculating cross products, you're probably used to expanding across row 1. So that's what I'm going to do. I'm going to take the first entry in row 1, column 1, and remember when we calculate a 3 by 3 determinant, I forget about that entry's column and that entry's row, and then I calculate the remaining little 2 by 2 determinant right here. Being careful with our brackets, I'm going to put the determinant, the minor 2 by 2 determinant in brackets. And we've got our forward diagonal product minus our reverse diagonal product. Okay? And then we're going to work our way across the matrix. So we're going to our second entry now, which is 2, but remember you change the sign of your second entry. So this is going to be minus 2 times the minor determinant of that entry. So I'm going to cover up that entry's column and row, and I'm going to calculate the little 2 by 2 determinant that's left. So that's going to contain the products, forward diagonal product -5 times 3 minus lambda minus reverse diagonal product 5 times -2. Okay, so we've got one more little minor entry to calculate. The third entry in row 1 is 2. I'm going to cover up its column and row and calculate the minor determinant. So I'm getting rid of this column and this row, and I'm calculating this minor 2 by 2. So this looks like -5 times 5 minus 5 times -4 minus lambda. All of that equal to 0. That is going to lead us to an algebraic equation that we can solve for lambda. It's just going to take a little bit of effort doing all the algebra. So I'm going to start by simplifying the bracketed elements first. I'm going to FOIL here. Demoting the brackets to parentheses. We're going to go back and combine like terms within parentheses, and I'm going to rearrange everything in descending order. Looks like the last two terms cancel, and so we just have to multiply this binomial times the trinomial. So I'm going to start by distributing the 3, and then distributing the lambda. And then we have a polynomial equation in lambda that we need to solve. This is a higher degree polynomial equation in lambda that we cannot factor by grouping. So you can use your rational zeros theorem and synthetic division to solve this polynomial equation. Now, I went ahead and typed in this polynomial function to my graphing calculator. And by examining the graph, we can see that it's got 3 distinct x-intercepts, -2, 1, and 3. So I'm just going to verify those as zeros of this polynomial using synthetic division. And I'm going to start with the eigenvalue 1. So to verify this, I'm just going to run through the synthetic division process. That confirms that it is a 0. And remember from the graph, -2 was also an x-intercept. So I'm just going to verify this at this point. That's also a 0. And the third 0 from the graph was 3. And I'm just going to verify that as well. At any point, especially once you get to this point, you can also convert it back to a quadratic and factor in the traditional way. But what we see here, we have three distinct real eigenvalues. The first one, lambda sub 1 is equal to 1, lambda sub 2 is equal to negative 2, and lambda sub 3 is equal to 3. Since we have three distinct real eigenvalues, we need to find the corresponding eigenvectors. So let's begin working on our eigenvectors. So we want to find the eigenvector v sub 1 corresponding to the eigenvalue lambda sub 1 equals 1. Now remember, the way that we find our eigenvector is by using this matrix equation. We need to solve A minus lambda I times eigenvector equals 0 vector for the eigenvector v. A minus lambda I is represented over here, in this case in determinant form. We're going to write it in matrix form. So we're going to be subtracting 1 along the diagonal of matrix A. So we have 3 minus 1, which gives us 2. The other entries are the same. The very center entry, negative 4 minus lambda, is negative 5. And our very last entry, so positive 3 minus 1 is equal to 2. Times eigenvector with 3 components equal to a 3 by 1 column vector of zeros. Now, this is also going to be a dependent system. Now, in order to solve this system, I'm going to use my calculator and the RREF function, reduced row echelon form, to solve the system. But we'll have to be able to interpret this because we are dealing with a dependent system with an infinite number of solutions. So this is what I'm going to type into my calculator, and then I'm going to put it in reduced row echelon form. Okay, so I'm going to pause the video while I enter the information into the calculator, and then we'll look at the result. All right, with the matrix plugged into the calculator, we are going to apply the reduced row echelon form function to what I have entered as matrix A. And the result looks something like this. Now remember, if there is one solution to the system, you'd have an identity, 3 by 3 identity matrix on the left and a column vector of solutions on the right. It's not exactly what we have here. It looks a little different than normal. So I'm going to record this as the solution. And then translate that back into what it represents. So looking at row 1, it represents V1 plus V2 equals 0. And row 2 represents V sub 3 equals 0. So for my eigenvector, which I'm calling V1, the third component is going to have to be 0. And the other two components just have to have opposite signs. So I could have, if I say vector v2 is 1, then vector v1 is negative 1. Or if I say the first entry is positive 1, the second entry has to be negative 1. Again, it doesn't matter as long as they have opposite signs. So we have one particular solution, x sub 1 of t, equal to e to the lambda t times eigenvector negative 1, 1, and 0. So there is one particular solution, and we need to find 3 more. So let's look at our second one. We're going to find second eigenvector v sub 2 corresponding to second eigenvalue lambda 2, which was negative 2. Okay? So we're going to set it up the same way, and we're going to run a shortcut on this one because we know how it turns out. We ended up putting A minus lambda I in terms of an augmented matrix. So I'm just going to update this for lambda sub 2 equals negative 2. So I'm going to use this as my guide to find the entries. The first entry is 3 minus lambda. 3 minus negative 2 gives me 5. So really, I'm just changing the diagonal values. Second entry, negative 4 minus negative 2 is negative 2. And then our last entry, 3 minus negative 2, gives me 5. So I'm going to update this information in my calculator. I'm going to go to my matrix edit. I've got the previous matrix entered. All I have to do now is change those diagonal values. So I'm going to change just the diagonal values. Makes for a quick, easy edit. I'm going to go back to my home screen. And I'm going to redo my reduced row echelon form for matrix A. And here is the result. Okay, so let's see what this looks like in terms of equations. So interpreting row 1, this says V sub 1 equals 0. And interpreting row 2, V2 plus V3 equals 0. So our second eigenvector, V sub 2, the first entry has to be 0, and for the second and third entries, they just have to have opposite signs. So if I say that V2 is 1, then V3 would be negative 1. Or if I say V2 is negative 1, V3 would have to be positive 1. Again, this is a dependent system with an infinite number of solutions, so we're just making sure that those patterns are there, even though details may be a little bit different. So our second particular solution is e to the negative 2t times eigenvector V2, which looks something like this. Okay, 2 down, 1 to go, same procedure. Next, we're going to find eigenvector V sub 3 corresponding to eigenvalue lambda sub 3 equal to 3. And we're going to set it up in an efficient way. So we're going to take, again, our matrix A minus lambda I, just updating our diagonal using 3 for lambda this time. So our entries would be 3 minus 0 is 3. Our middle entry, negative 4 minus 3, that would give us a negative 7. And our last entry, 3 minus 3, again would be 0. Okay, so we will update this in our calculator. Whoops, first entry, 3 minus 3 should be 0. Did y'all catch that? I bet you did. Okay, got it just in time. Let's update the entries in our calculator. I'm going to go back to my matrix menu and edit. Again, all I have to change are the diagonal values. And the shortcut on my home screen, I'm just typing second entry to recall the command reduced row echelon form to A. And this is our result. Let's convert those into equations. Row 1 says V1 minus V3 equals 0. This implies that V1 and V3 have to have the same value. And row 2, V2 plus V3 equals 0, which implies V2 and V3 have to be opposite signs. So if we say that this is going to be eigenvector V3, let's say V3 equals 1, then V2 would be negative 1 and V1 would be 1. So our third particular solution is e to the 3t times eigenvector 1, negative 1, and 1. So we have 3 linearly independent particular solutions, so we can assimilate these to make our general solution. Okay, so I bet I can fit it in right over here. Our general solution then, x is going to be c1 x1 plus c2 x2 plus c3 x3. Thus, our general solution, x of t, looks like c sub 1 times our first solution, that was e to the t, times negative 1, 1, 0, plus c sub 2 times x2, That was e to the negative 2t times 0, 1, negative 1. And finally, c sub 3, e to the 3t times eigenvector v3, 1, negative 1, and 1. Okay, so that's our general solution in matrix form. But if you're a little unfamiliar with matrix form, let's go ahead and translate this into 3 equations, 3 variables. Sorry about running out of room here. I'm going to write it really small over here. So looking across row 1, we have negative c1 e to the t, 0 times c2, and c sub 3 e to the 3t. Looking across row 2 for each matrix, we have 1 times c sub 1 e to the t plus c sub 2 e to the negative 2t minus c sub 3 e to the 3t. And finally, x sub 3 of t, looking across row 3, 0 times c1, negative c2 e to the negative 2t plus c3 e to the 3t. So this is the matrix form of our general solution, and this is a more traditional approach to expressing the general solution. Now keep in mind, whenever you're working on your homework and you're checking your answers in the back of the book, the details may be slightly different. Here's how to make sure that what you've done is correct. For example, if I look right here in equations 1 and 2 and I compare these two terms, what I'm looking for there is that the coefficient of e to the t in the first equation must be the opposite of the coefficient of e to the t in the second equation. So if, for example, you have a negative 2 here and a positive 2 here, then you still have the right answer. Because remember, this is a general solution. So if I were to apply some initial conditions and turn it into a particular solution, then those C's would have no ambiguity. There would be one exact expression for the particular solution. So look for relationships whenever you check your work in the back of the book. Okay? Let's apply this new method to an old problem. Example 3 should be familiar. We've been really focusing on 2 applications, our spring mass systems and also our fluid flow or our solution mixing problems. Example 3, let x sub 1 of t and x sub 2 of t be the amount of salt in the brine tanks shown below. So the first tank there is on the left. The amount of salt in tank 1 will be measured by x sub 1 of t. That will usually be in pounds, something like that. X sub 2 of t is the amount of salt in tank 2. Now, the model for the system is given to the right. What we have here, if you'll remember, is Ricci-Rocco, right? Rate in, concentration in, minus rate out, concentration out. It's just given in a very general form here. So the rate of change of brine in tank 1, dx sub 1 over dt, is equal to the rate coming in times the concentration coming in, minus the rate coming out times the concentration coming out. And I have the same thing for the second equation. This would be the rate coming in, concentration in, minus rate out, concentration out. The first equation is a little bit out of order intuitively, just so that we can have our system in standard form, our x sub 1s and x sub 2s lined up. Now, assume that both flow rates are 10 gallons per minute. So I've got brine flowing from tank 2 to tank 1. That's going to be 10 gallons per minute. And flowing back from tank 1 to tank 2, that's 10 gallons per minute. So keep everything uniformly mixed. Find x sub 1 of t and x sub 2 of t. Given initial conditions, the amount of salt in tank 1 is 15 pounds initially and 0 pounds in tank 2. The volume in tank sub 1 is 25 gallons and the volume or capacity in tank 2 is 40 gallons. So let's go ahead and set up our system using our Ricci-Rocco. So the rate of change of salt coming into tank sub 1, I'm going to call it x sub 1 prime, is equal to the rate in times concentration in. So coming in to tank 1, the rate coming in is 10 gallons per minute times the concentration coming in? Well, it's going to be the amount of pounds of salt in tank 2 per 40 gallons. That's rate in, concentration in. Now, still focusing on tank 1, what's coming out of tank 1? Well, it's coming out at a rate of 10 gallons per minute, and the concentration out is the amount of salt in tank 1 per 25 gallons volume or capacity. Okay, again, notice the order of our variables there. We're kind of going with the intuitive approach, but we need to remember that when we write this in matrix form. Focusing on tank 2, the rate coming into tank 2 is 10 gallons per minute, and the concentration coming in is from tank 1, which is X sub 1 pounds of salt per 25 gallons. The rate coming out of tank 2 is 10 gallons per minute, and what's going out is X sub 2 pounds of salt per 40 gallons. We can go ahead and simplify this and write this in matrix form. So we could say X bar prime is equal to, let's work on our coefficient matrix and be really careful here because I have to have my matrices in standard form. So I'm going to start with the coefficient of X sub 1, 10 over 25, that reduces to 2/5. And then I'm going to work on coefficient of X sub 2. And I missed a negative. Let me go back and get a negative. There we go. But you noticed. And then right here, 1/4. Okay? And then the other two are already in order. So coefficient of X1 in equation 2 is 2/5. And coefficient of X2 in equation 2 is negative 1/4. So there is our matrix equation. And from this, we need to derive our characteristic equation. So our characteristic equation for a system is determinant of A minus lambda I equals 0. So we have determinant of A, negative 2/5 minus lambda. And remember, A minus lambda I results in looking like subtracting lambdas along the diagonal of matrix A. Okay, let's find this little 2 by 2 determinant. We take our forward diagonal product minus our reverse diagonal product. Let's carry out the FOIL. Let's see, that would be positive 1 over 10. Outside terms plus 2 lambda over 5. Inside terms plus lambda over 4. Last, lambda squared. And then we have another minus 1/10. So it looks like our 1/10ths cancel. Let's combine like terms, starting with lambda squared. 2/5 plus 1/4. Y'all can probably do that in your head, but I got to work it out here. Looks like 13 lambda over 20. So this will be a pretty easy characteristic equation to solve. I can factor out the greatest common factor, lambda. And we're going to get two distinct eigenvalues. Let's call lambda sub 1, 0, and we'll call lambda sub 2, negative 13 over 20. So those are our two eigenvalues. We need to find corresponding eigenvectors. So I'm going to try and use all my space here. And let's find lambda 1. Our first eigenvalue is lambda sub 1 equals 0. We need to find its corresponding eigenvector. So the way that we do that is by solving the matrix equation A minus lambda I times vector V equals 0 vector. So A minus lambda I, we're plugging 0 in for lambda in this A minus lambda, okay? So subtracting 0 along the diagonal does not change matrix A. We're going to end up with elements negative 2/5, positive 2/5, 1/4, and negative 1/4 times eigenvector with components v1, v2 equals a column vector of zeros. Now let's put these in equation form. In equation form, that's negative 2/5 v1 plus 1/4 v2 for equation 1. That is row 1 times column 1. And notice if I did row 2 times column 1, I would end up with the same equation, different by a multiple of -1. So let's get V1 in terms of V2, or vice versa. Let's go with positive coefficients here. So I'm going to add V1 to this side. I'm going to multiply both sides by 4. Okay, now I can say at this point, let V1 equal 1. That would be perfectly acceptable and it would lead me to the correct answer. But I want to choose something really convenient. Remember, we're dealing with a dependent system here, an infinite number of solutions. I'm just trying to find one representative of the solution. So if I say that V1 is 5, do you see why that's a convenient choice? Then V2 would also be an integer, okay? So our first eigenvector, V sub 1, is going to have components 5 and 8, and our first particular solution then would be e to the 0t times 5 and 8, or just the constant vector 5 and 8. Okay, let's find our second eigenvector. Case 2, we want to find eigenvector V2 corresponding to our second eigenvector, which was what? -13/20. Okay. So we need to work on a minus lambda I. So I'm going to subtract -13/20 from those diagonals. My brain's tired. I'm going to get my calculator ready. So I'm going to take first entry, -2/5 minus -13/20. And I end up with an easy 1/4. Whoops. And last component, -1/4 minus -13/20 gives us 2/5 times V1, V2 equals zeros. Okay, so notice if I translate row 1 times column 1 back into equation form out of the matrix, I'm going to get 1/4 V1 plus 1/4 V sub 2 equals 0. So solving for V1 in terms of V2, I get V1 equals -V2. That's exactly what that second equation would give me. That would get the same relationship between V1 and V2. So it's only necessary to look at that first one. So I'm going to choose something convenient. Let's suppose our second eigenvector, if we say that V2 is 1, V1 would be -1, okay? Or if I say that V2 is -1, V1 would be +1. Just have to make sure that they have opposite signs. Therefore, our entire particular solution, x sub 2 of t, is e to the -13t/20 times the eigenvector -1, 1. Okay, that's our second particular solution. So now we're ready to express the general solution to the system. So our general solution is going to take the form x equals c sub 1 x sub 1 plus c sub 2 x sub 2. So working this out with details, remember our first solution had e to the 0t, which is 1. I'm going to leave it out in this case and just use the eigenvector 5, 8. Plus c sub 2 times our second particular solution that we found up here, e to the -13t/20 times -1, 1. Okay, so that is the matrix form of our general solution. But to make it sense with what we're most familiar with, let's rewrite this in terms of two distinct equations. So the first function in this matrix equation is going across row 1, 5c1 minus c2 e to the -13t/20. And the second equation, x sub 2 of t, is 8c1 plus c sub 2 e to the negative 13t over 20. That's our general solution in traditional equation form. Now, hang in there. We're almost done, but did you remember we have initial conditions to deal with? So we need to come back up here and apply our initial conditions. In tank 1, there's initially 15 pounds of salt, and tank 2, 0 pounds of salt. We can expect the amount of salt in each tank to equalize over time, but let's apply these initial conditions to our solutions. So initial conditions, x sub 1 of 0 is 15, x sub 2 of 0 was 0. So working with our first initial condition, I'm going to set x1 equal to 0, and I'm going to plug 0 in for t. That's going to give us 5c1 minus c2. Setting our second equation equal to 0 and plugging 0 in for t, we end up with this equation right here. You can solve this with RREF on your calculator, but also remember you're free to do the algebra. This one is a piece of cake with the algebra. Notice I can add those two equations together and very quickly get C1, right? And then C2, I'm just going to use the second equation. C sub 2 is negative 8C sub 1. Just rearranging that second equation. So plugging in what we know about C sub 1, we end up with negative 120 over 13. Okay? Therefore, our particular solution to the original problem is now x sub 1 of t equals 5 times c1, that's 75 over 13, minus c2, or plus 120 over 13, e to the negative 13t over 20. And x sub 2 of t is 8 times c1. Another 120 over 13. Did I just do that? That's a long memory, isn't it? Plus c2, that's minus 120 over 13, e to the negative 13t over 20. So we have a new solution to an old problem, solving our tank mixing problem with eigenvalues and eigenvectors. We have one more case to talk about, and that is complex eigenvalues. Suppose the characteristic equation, determinant of a minus lambda I equals 0, has complex conjugate eigenvalues, lambda and lambda bar, equal to p plus or minus qi. Now, in this case, the bar on the lambda does not indicate a vector. It indicates a complex conjugate. So that is simply lambda equals p plus qi and lambda bar equals p minus qi. Then there exists complex conjugate vectors of the form v and v bar equal to a plus or minus bi. Now, in this case, the bold print indicates that we are dealing with the vector, and the bar indicates that we're dealing with a complex conjugate vector. To obtain our solution, we can choose one of the pair. Choose lambda and v to obtain the following. X of t equals a plus bi. Notice the bold print on the a and b. That indicates that we're dealing with vectors. Times e to the p plus qi times t. So notice we have chosen 1/2 of our complex conjugate pair. We happen to choose the one with the plus. And here we've also chosen 1/2 of our complex conjugate pair. You can choose either of the two and come up with your solution. Now, we're going to apply Euler's formula to the exponential like we did in Unit 2. So this is e to the p times t times cosine of qt plus I sine of qt. Now, we learned in chapter 2 that the real part and the imaginary part are linearly independent particular solutions, so their linear combination is also a solution. What that means is essentially we lose the I in our general solution. So let's develop that a little further here. What I want to do next is FOIL these two terms and rearrange them into real and imaginary parts. So I'm going to factor the e to the p to the left, and then let's go ahead and FOIL. So we have first two terms, a cosine of qt, plus outside terms, I times a sine of qt, inside terms, ib cosine qt, and last, notice we have an I squared there, so that gives us minus b sine of qt. And then let's separate it into real and imaginary parts. So starting with the real parts, we have a cosine qt minus b sine qt. That's going to be the real part. And then for the imaginary part, we're also going to factor out the I. So leftovers inside brackets here would be a sine qt plus b cosine qt. So our general solution here has two parts. This is what we're going to call the real part. And this, without the I, is called, of course, the imaginary or complex part. As we saw in section 2.3 for complex conjugate roots for a single differential equation, the real and imaginary parts of the solution are linearly independent solutions. So what that means is we're going to define two linearly independent solutions as derived from our general solution with two parts up here. Let's call x sub 1 of t the real part of x, which would be e to the pt times a cosine qt minus b sine of qt. And x sub 2 of t, those need bars, will be the imaginary part of our general solution without the I. That's e to the pt times a sine qt plus b cosine qt. So here's what I want you to know in practice. When you come up with a complex conjugate pair of eigenvalues, choose 1/2 of the pair to use in your exponent. Second, the real part and imaginary parts can be separated as two linearly independent particular solutions. Thus, their linear combination is also a solution. So ultimately, you end up with a general solution that does not have that coefficient I. Now, it's actually easier in practice than what the development looks like. So let's try an example. And by the way, you will have one problem on your homework that deals with imaginary eigenvalues. So as we did before, we're going to start by expressing our system in matrix form. So let's pick up our coefficients. There is our matrix equation, and of course this coefficient matrix is matrix A. So let's find our characteristic equation, which is determinant of A minus lambda I equals 0. So we have learned that turns out to look like subtracting lambdas along the main diagonal. And calculating our 2 by 2 determinant, we have 1 minus lambda times 1 minus lambda minus 2 times negative 2 equals 0. Foiling, we obtain 1 minus 2 lambda plus lambda squared plus 4 equals 0, or lambda squared minus 2 lambda plus 5 equals 0. This quadratic cannot be solved by factoring, so we can go ahead and apply our quadratic formula. We'd end up with lambda equals negative b plus or minus the square root of b squared minus 4ac all over 2a, or inside parentheses there, notice we have 4 minus 20, which gives us negative 16. Square root of negative 16 is 4i. So our complex conjugate pair looks like 1 plus or minus 2i. So we have two distinct complex conjugate solutions for our characteristic equation. Now, we are going to choose one of those solutions to work with, 1/2 of our pair. And let's choose lambda equal to 1 plus 2i. Then I'm going to plug this into our equation, our matrix equation, a minus lambda I times vector v equals the 0 vector. Our goal here is to find a corresponding eigenvector, right? So plugging 1 plus 2i in for lambda in this equation over here, 1 minus 1 cancels out. We end up with negative 2i here, and the same thing here as well. Finishing out our matrix equation, notice our two rows are very similar. They're going to give us the same result, so it's only necessary to consider one equation. Row 1 times column 1 ends up looking something like this. And I can get one of these values in terms of the other. So solving here for vi, I'm going to divide both sides by negative 2, and then I'm going to divide by I. So we have negative v sub 2 over I. Notice if we rationalize the denominator, we end up with negative v2 times I over negative 1, or let's simplify to v2 times I. Let's choose a convenient value for v2, such as I. Remember, at this point, we're dealing with a dependent system with infinite solutions, so I need to find one representative of the solution. Let's let v sub 2 equal I. Then v sub 1 equals I times I squared, or negative 1. So our corresponding eigenvector v is v sub 1 equal to negative 1, v sub 2 equal to I. So notice I have an imaginary part to my eigenvector. So let's use this eigenvector to begin expressing the solution to the system. So back to our solution to the system, we have e to the p, remember we chose 1 plus 2i times t, times our eigenvector, negative 1 and I. Let's expand our exponential with Euler's formula. We have e to the t times cosine of 2t plus I sine of 2t. So the real part of my imaginary number is the coefficient of t here, and the coefficient of I goes into the argument of our trig functions. And we need to record our eigenvector here, negative 1 and I. I think it would be helpful if we express this as two individual solutions. So let's look at what's in row 1 here. So x1 of t is equal to, multiplying row 1 by column 1, we have e to the t times negative cosine of 2t, and notice here we're going to have I times I, which is I squared, or negative 1 sine of 2t. Do brackets here, make it a little more readable. So there's the first solution, and x sub 2 of t. Now let's go ahead and expand the exponential according to Euler's formula. So the real part becomes the coefficient of t in the exponent, and the imaginary coefficient becomes the argument, cosine of 2t plus I sine of 2t. Okay, so there would be row 1, that's x sub 1, and x sub 2 then would be, so let's go ahead and multiply the exponential into our matrix. So we have negative e to the 1 plus 2i times t, and I e to the 1 plus 2i times t. We can expand both of those according to Euler's formula to obtain. Now, we got to make sure and distribute this negative out here. E to the t times cosine of 2t plus I sine of 2t. And for the second one, we're going to have I times e to the t cosine of 2t plus I sine of 2t. Simplifying, we have no change up here. And down here, distributing the I, we have e to the t times I cosine of 2t plus I squared, or minus 1 sine of 2t. So the idea with these imaginary coefficients is I can rearrange it and I can have the first particular solution corresponding to the real part and the second particular solution corresponding to the imaginary part. So one particular solution, x sub 1 of t, then is going to consist of the real parts, which looks something like this. So I'm going to write it as e to the t times negative cosine of t, make my vector a little bigger here, negative sine of t. And my second solution, x sub 2 of t, is going to be the imaginary parts. So that's going to be e to the t times sine, need a negative, sine of t and cosine of 2t. That one should be 2t as well. Okay? And I'm run out of space. I'm sure that you have to make the conclusion. Then we could say the general solution is c sub 1 x sub 1 plus c sub 2 x sub 2, using these two particular solutions as x1 and x2. If we wanted to turn it into a particular solution, then we would also need initial conditions. So once again, the idea is if you get complex solutions to your characteristic equation, choose one half of the pair, use that to find a corresponding eigenvector, which will likely have imaginary components. Then you can expand your two solutions and separate the real part into one particular solution and the imaginary part into another particular solution, not including the coefficient I. Those two are linearly independent solutions, therefore their linear combination is also a solution. You end up with a general solution that does not have imaginary coefficients. Again, you will see one example like this on your homework. Please focus on mastering those that have a characteristic equation with real solutions. Okay, best of luck on your homework.